In today's video, we're going to start by looking at exponential functions. This is just the first part of our exponential functions topic that we're going to look at in this course. But I want to look at exactly what an exponential function is, and then look at some of the graphs of these exponential functions and then transforming them to see what they would look like. After that, in the next video, we will look more at actually drawing them more accurately, and if you're given a particular exponential function, can we find the asymptotes, etc. But we will look at that in our next video. But to start with, what is an exponential function? Well, I'm going to quickly look at something that is of the form 2 to the power p over q. Okay? This is just a random expression, okay, where p and q are going to be whole numbers. There's two ways that you can evaluate this. Okay, I can either look at 2 to the power p and then take the qth root of that value, or I can take the qth root of 2 and then take that to the power p. So there's two different ways I can evaluate this one particular expression. The other thing that we have to be aware of is if p is negative. If p is negative, so it's really 2 to the power negative p over q, then of course that's the same thing as saying 2 to the power p over q and then doing 1 divided by that amount. That is if that is a negative. So there's different ways that we are evaluating this. This can all be done normally if it's decent numbers where you're just taking like a square root or a cube root or something easier and you're dealing with pretty easy numbers. You can do this in your head or just with simple pen and paper. But if you ever end up with 2 to the power something that is an irrational number, okay, remember we're doing 2 to the power of a rational number here, but if I was doing 2 to the power of an irrational number, then you need a calculator. An irrational number is just a number that can't be written as a fraction. So obviously you can't do that in your head and you would need to use a calculator. What does the graph of something like this look like? Well, if I take, we'll assume that we're looking at f of x is equal to 2 to the power x. Roughly what does a sketch of that graph look like? It actually looks something like this, where it passes through the point 0, 1. Okay, how do we know this? We can look at this just by plugging in larger and larger and larger values of x, and you'll find, and this is said a lot whenever you get a number to a certain power and you increase that power, you say that it actually increases exponentially, meaning that the larger that you make x, the quicker and quicker this thing's going to shoot upwards. Okay, exactly what's happened here. You start off with a pretty shallow rate of increasing, as you see on the left hand side of this graph, and then as you go towards that right hand side and x goes more and more and more towards infinity, this thing actually goes towards infinity faster. So you can see that this would be the case for this particular function. If I plugged in x is equal to 0, anything to the power 0 apart from 0 itself, any number to the power 0 is just 1. So we know that it must go through the point 0, 1. What happens if we were to change the base? So I've just taken 2 as a base here throughout all of this. What happens if we change the base? I'm going to look at a couple different possibilities for a base here. So let's say I'm looking at, we'll start with saying that I'm looking at f of x is equal to a to the power x. Okay. Now I'm going to look at a couple different options here. For a equal to 0, okay, I'm looking at 0 to the power x. 0 to the power x is always equal to 0 as long as x doesn't equal 0. whatever value I make x, as long as it's not 0, I'm still going to get 0 to the power of anything is 0. Okay? 0 to the power 0 is actually undefined. So you end up with this really weird situation here where you're going to end up with just this straight line because it's always going to equal 0. It's not going to look anything like what we just had here because 0 to the power of any x value is still 0. Okay? So you're just going to end up with this horizontal line and it's not going to be defined at the origin. Okay? Where x is equal to 0, you're going to have this point where it's undefined. Because it looks nothing like what we're used to back here with this particular exponential graph that we've looked at with a base of 2, because it looks nothing like this, we actually don't ever consider a base of 0, because it's nothing like what we're used to. Now let's look at a being negative. Okay? So for example, we're looking at negative 2 to the power x. Okay. What issues arise here? What if x is anything like 1/2, 1/4, etc.? You end up taking an even root of a negative number, which you cannot do. Okay, I can't square root a negative number. So if I ever ended up with negative 2 to the power of 1/2, that's the same thing as saying I'm taking the square root of negative 2. Okay? That's not a real number. So we don't consider that. So because I fall into this trap with a being a negative base, okay, so I'm taking a to be a negative number, and then taking it to any power I like, any x I like, I end up with a bunch of x values for which the value is actually undefined. The function value is undefined because I'd have to go into the complex plane in order to define it, which we don't do here. I'm just looking at real numbers. So I end up with a bunch of values for which it's not even defined. So we never consider a negative base either. So because the function value f of x would not be a real number for so many x values whenever you take an even root, we're not going to look at a being a negative number either. So we're not looking at negative bases, and we've already said we're not looking at a 0 base. So now I'm just looking at a being greater than 0. Okay? But there's one more number that I don't really want to ever consider as a base for any of my exponential functions. And that is a is equal to 1. What happens when a is equal to 1? Well, I end up with 1 to the power x. 1 to the power x, no matter what value x is always equal to 1. So again, I end up with a similar situation that I had in my first case when a was 0, where I just end up with this straight line, okay, that looks nothing like any other exponential function, okay, when I've taken a to be a different number. So I'm not even going to consider a being 1 either, because it's not ever going to look like the rest of our exponential functions. So for this reason, it doesn't look like other exponential functions. So we don't consider a is equal to 1. Okay. So therefore, whenever I've got my function f of x is equal to a to the power x, I'm only ever going to consider, so it is an exponential function where a is either between 0 and 1, so a is either greater than 0 and less than 1, or a is strictly greater than 1. So again, I'm not considering 0, I'm not considering 1, and I'm not considering anything less than 0. I'm not considering the negatives. So we always consider an exponential function to look like f of x is equal to a to the power x. Remember, x is our variable, and a can be whatever number we like as long as it falls into one of these two parameters. So either a is between 0 and 1, or a is greater than 1. If that is the case, we have an exponential function on our hands. So for example, f of x is equal to a half to the power x, that's an exponential function, or f of x is equal to 4 to the power x, that's an exponential function, but f of x is equal to negative 4 to the power x is not an exponential function. Okay. So in order for it to be an exponential function, they are the parameters that we need. So like we said right at the start, we looked at this particular exponential function of 2 to some power, okay, to a power x. That's an exponential function, and we looked at its graph of what it would roughly look like, okay. X doesn't need to be a rational number. We look at x being rational numbers in terms of actually plotting points that we would know, but x can be any real number whatsoever. Okay. I just started out with rational numbers just so we can kind of see what was going on. Okay. Depending on what a is, so whether a is between 0 and 1 or a is greater than 1, will depend on what the graph looks like. Okay. We've already seen what the graph would roughly look like if a was greater than 1. So as we see here, we have this particular graph where it rises as you go from left to right. It goes through the point 0, 1, and that is the case if a is greater than 1. Whenever a is greater than 1, it will take on that same shape, okay, where it rises as you go from left to right, and it will go through the point 0, 1. Okay, so when a is greater than 1, that's what it looks like. What happens if a is between 0 and 1? Okay. Well, if a is between 0 and 1, think about, for example, like we said before, f of x is equal to 1/2 to the power x. Okay, so in this case, a is between 0 and 1. What happens is x increases. Well, as x increases, I'm going to get a smaller and smaller and smaller fraction. Okay, you can see this just by using small values of x, because if x was 1, I would end up with f of x was 1/2. If x was 2, then my function value is 1/4. Well, 1/4 is less than 1/2, therefore I'm getting smaller as x is getting larger. Again, when x is 0, I still get 1. Anything to the power 0 is 1 apart from 0. So I know that I'm still going to go through that point 0, 1, but this time I'm going to fall as x gets larger. Okay. So as x gets larger and larger and larger and goes towards infinity, I know that I'm going to go towards 0 because my fraction gets smaller and smaller. What happens as I go towards negative infinity? Well, remember, if I ever have a negative power, all it's going to do is flip the fraction. So by doing that, I would actually end up with a number greater than 1 to a power going towards infinity, meaning that it gets larger and larger and larger going towards infinity as x goes towards negative infinity. So as x goes towards negative infinity, my function goes towards infinity. So I actually end up with a situation like this, where again I still go through 0, 1, but I can see as x goes towards infinity, my fraction gets smaller. As I go towards negative infinity, it's the same thing as flipping my fraction and going towards infinity, okay, because I'm just taking 1/2 to a negative power. Okay, so I flip the fraction and then it would take x going towards infinity, which would then take my whole thing towards infinity. So I end up with this kind of situation here. What is my domain and range for each of these? My domain is all real numbers, okay? I'm defined everywhere. No matter what the value of x is, I can always find a function value for a to the x. What about my range? Okay. I know that I can't go below 0. It turns out that 0 is actually an asymptote. Y is equal to 0 is an asymptote. I can get really, really, really close to it, but I'm never actually going to hit it. So my range, we say, is going as close to 0 as you possibly can, but not including 0, up to infinity, because remember, this thing shoots off towards infinity in the y direction. Same thing here. My domain is all real numbers, and all you see here is that my graph has been flipped in the y-axis. So my range, again, is 0 to infinity. I get really, really close to 0, but don't quite get there, and I shoot up to infinity this time as x goes towards negative infinity rather than positive infinity. Okay. And like I said, we have this horizontal asymptote in both cases, and the horizontal asymptote is just y is equal to 0, and that is the same in both cases. Let's go ahead and sketch some of these graphs. Okay. The first one that I want to look at is going to be f of x is equal to 6 to the power x. Okay. Whenever you get one of these, what I would always do is plot out 3 points, okay, to give you a slightly more accurate sketch. And these are the points that I would always go ahead and graph. I will graph where x is 0, where x is 1, and x is negative 1. When x is 0, we know that f of x is 1, because 6 to the power 0 is 1. How about when x is 1? 6 to the power 1 is 6. How about 6 to the power negative 1? Okay, 6 to the negative 1 is the same thing as saying 1 over 6 to the 1, which is just 1 over 6. Okay, remember, a negative will flip the fraction, okay, and give you the reciprocal. So when we go ahead and draw this, we can see that in this case a is greater than 1, a is 6, so I know that it's going to take on this kind of shape. I know it's going to go through the point 0, 1, and I can actually now plot 2 other points on my graph, being 1, 6, and negative 1, 1 over 6. Okay. I can see as x goes towards infinity that f of x also goes towards infinity, and as x goes towards negative infinity, remember, it's the same thing if I've got 6 to the power of a negative number, it's going to be 1 over 6 to the power of the appropriate positive number, okay? Which means that I'm going to get 1 over a larger and larger and larger number, sending me towards 0. So as x goes towards negative infinity, f of x goes towards 0. Another example that we can do is looking at f of x is equal to 1/2 to the power x. What does this look like? Again, I would plot out 3 points. When x is 0, when x is 1, and when x is negative 1. Okay. When x is 0, we know that f of x is 1. When x is 1, I just get 1/2 to the power 1, which is still 1/2. And then when x is a negative 1, it would be 1/2 to the power negative 1, which is the same thing as saying 2 to the power 1. Remember, we flip the fraction and then take it to the positive power, so it would be 2 over 1 to the power 1, which is just 2. So I again end up with 3 points that I can plot. Okay. I know that A is between 0 and 1, so I'm going to end up with this kind of a graph. I go through the point 0, 1. I also go through the point 1, 1/2, and I go through the point negative 1, 2. Okay. The other thing that I want to look at in this particular video is actually looking at shifts of these graphs, okay? So I want to see what happens if we reflect, if we shift up, shift down, whatever. What I would always do whenever you do this is I would track the point 0, 1, I would track one other point on the graph, and I would track the horizontal asymptote y is equal to 0. That will help you get a more accurate picture for a sketch of this graph, okay? So track the point 0, 1, track one other point on the graph, whichever one you choose, and then track that horizontal asymptote, okay? The reason that I would track one other point other than 0, 1 is sometimes you may end up with some stretching happening, okay? And it will help you kind of plot out what that stretch may look like. It only has to be a sketch, it doesn't have to be anything crazy or whatever, but by providing that one other point, it will show any stretching that's happening. Okay. First example I want to look at is to sketch the graph of f of x is equal to negative 2 to the x plus 4. Okay. So I've taken my exponential function 2 to the x, then I've got a negative in front of that, okay? I've not got 2 to the power negative x, I've got negative 2 to the power x. You can even add in parentheses here to help you. So I've got the negative outside the function, okay? Because it's outside the function, it means it's doing something vertically, not horizontally. So what that negative outside the function does is it's actually going to flip that graph in the x-axis. Okay, so the negative on the outside will flip the graph of 2 to the x in the x-axis, and then I move the whole graph up by 4 units. Okay, so I'm going to flip 2 to the x in the x-axis, and then move up by 4 units. So what happens here? Well, my asymptote, when I flip over the x-axis, well, the asymptote is the x-axis, okay? So all I'm doing here is I've just flipped the graph in that line y is equal to 0. So for my first translation, my horizontal asymptote is going to stay where it is. But then I'm moving my whole graph up by 4 units. So my horizontal asymptote is now at y is equal to 4. Okay. Let's see what happens to the point 0, 1. Okay. The point 0, 1, when I flip it in the x-axis, is going to go to the point 0, negative 1. And then moving it up by 3 units is going to go to 0, 3. Let's check out one other point. Let's look at the point 1, 2. Okay, that lies on 2 to the x because 2 to the power 1 is 2. What happens to the point 1, 2? Okay, well, when I flip it in the x-axis, it's going to go to 1, negative 2. And when I move it up by 4 units, it actually stays where it originally started from. So I still end up at 1, 2. So if I go ahead and draw a quick sketch of this, okay, I've got my x and y axes. My horizontal asymptote is now at y is equal to 4, so I'll plot that out. My horizontal asymptote is here. And remember, my graph was flipped in the x-axis, which means it now looks something like this. Okay, because I flipped it in the x-axis and then moved it all up by 4 units. I know that my point 0, 1 went to the point 0, 3, and I also have that point 1, 2. So this is now a quick sketch of f of x is equal to negative 2 to the x plus 4. The last example that I want to look at in this section is going to be this function. F of x is equal to 1/2 x plus 2 plus 1. Okay, this time that plus 2 is inside our function, okay, it's with x, which means that something happens horizontally. I'm going to shift to the left by 2 units, and then I have this plus 1 at the end, which is going to shift everything up by 1 unit. Now, shifting to the left by 2 units doesn't affect where my asymptote is, so it's still going to be at y is equal to 0, but then I have that plus 1 at the end, which means that my horizontal asymptote is now going to be at y is equal to 1. Then let's see what happens to that point 0, 1. I shift to the left by 2 units, meaning that it goes to a negative 2, 1, and then I'm going to shift up by 1 unit, so it goes to negative 2, 2. And then I can pick any other point that I want to on this particular graph. You can track the point 1, 1/2, that's on the original graph. Okay, I shift to the left by 2 units, which means that it goes to negative 1, 1/2, and then I shift up by 1 unit, so it's going to go to negative 1, 3 over 2. So now I can go ahead and sketch out this graph. Now I start out with the graph of 1/2 to the power x, so I know that it's going to fall as I go from left to right. I've then shifted to the left by 2 units and then shifted up by 1 unit. So I know that my horizontal asymptote is now at y is equal to 1. And then when I draw out this graph, I end up with something like this. And we said that 2 points that this particular graph goes through are negative 2, 2 and negative 1, 3 over 2. So I've got negative 2, 2 and negative 1, 3 over 2. You can pick another point to plot if you particularly want to. You could see what that y-intercept is if you want. That would be at 5 over 4, because it would be 1/2 to the power 2, which would be 1/2 squared, which is 1 over 4, and then adding 1 to that would be 5 over 4. So this point here is 0 and 5 over 4. Like I said, you can pick whichever points you want. You didn't necessarily have to do that third point, it's just that I looked at what the y-intercept might be. But as long as you have 2 points plotted and you have that asymptote, then that is a good enough sketch for the exponential graph.